Welcome everyone to The Explainer. I'm Dr. Chem. Today we're taking a breathtaking journey, soaring from the heavy emissions of bustling, traffic-filled cities, all the way to the absolute contrast of pristine, clean air forests. We're stepping into the modern laboratory to decode the invisible world of air quality. You know, we are constantly swimming in an unseen ocean of gases and microscopic particles. But how do we actually capture and measure the very air that's keeping us alive? Well, in this explainer, we're going to use some truly advanced science to make the invisible visible.
Here is our roadmap for today. First, we'll be decoding the AQI. Second, the 5 major pollutants. Third, the sides of measurement. Fourth, health risks and caution. And finally, personal sensors and apps. Let's dive right in. Let's kick things off with a crucial baseline definition, the Air Quality Index, or the AQI. Think of this as the ultimate definitive yardstick used by environmental and health agencies to tell us whether it's actually safe to be outside. It's a standardized scale running from 0 to 500, and it's designed specifically to communicate outdoor air quality and the health concerns that come with it directly to all of us. And hey, this isn't just some hyperlocal issue. As you can see from the WHO Global Air Quality Guidelines, managing air pollution is a massive, highly coordinated global health priority. We're talking about over 6,000 cities across 117 countries routinely monitoring their air. It's a universal challenge, which is exactly why having standardized measurements is just absolutely critical for global public health.
Okay, Section 1, decoding the AQI.
What's genuinely brilliant here is how universally understood these 6 color bands are. They perfectly map out our health risks. They range from a safe, green, good level between 0 and 50, all the way up to a hazardous, maroon emergency level at 301 and above. For any given pollutant, an AQI value of 100 is basically the tipping point. Anything below 100, you're generally good to go. But once you cross into that orange zone, the air starts becoming unhealthy, first for sensitive groups, and then literally for everyone as the numbers climb into red, purple, and maroon.
Moving right along to Section 2, the 5 major pollutants. So if we visualize the atmosphere with these incredible 3D animations, you'll see exactly what our advanced monitoring stations are constantly sniffing the air for. The EPA regulates these 5 major culprits under the Clean Air Act. We've got ground-level ozone, particle pollution, carbon monoxide, sulfur dioxide, and nitrogen dioxide. These are the usual invisible antagonists behind almost every single air quality warning you get. Let's zoom way in, microscopic level, on one of the most notorious offenders, particle pollution. Now, the absolute crucial distinction here is size. PM10 refers to particles 10 micrometers or smaller. They're tiny and, yes, inhalable. But PM2.5, that is microscopic. We're talking a fraction of the width of a single human hair. PM2.5 is far more dangerous simply because it can easily bypass your body's natural defenses, bury deep into your lungs, and even slip directly into your bloodstream.
Which brings us to Section 3, the science of measurement.
Step into the modern lab with me for a second to look at the ingenious physics of these active measurement monitors. It all centers on a device called the inlet head. Ambient air is forced through a system of tubes. Then, the air is forced to make a sharp turn. Thanks to simple centrifugal force, the heavier PM10 particles literally crash into and get trapped on impact plates. But those lighter PM2.5 particles? They effortlessly make the turn, passing straight through to a high-tech filter for incredibly precise weighing. It's essentially an elegant physical sorting machine operating non-stop out in the field. Now, after figuring out how to capture these particles, the next big puzzle is where to actually measure them. The EPA uses 4 specific geographical scales: micro, middle, neighborhood, and urban. Think of it like a scientist mapping out a sprawling environment. They want to perfectly match the monitored air with the highest population densities and the most severe expected pollution zones, from a busy roadside up to a 50-kilometer urban expanse.
But scientists don't just guess where to put these sophisticated stations. They use a fascinating meteorological tool called a windrose diagram. This visually maps out the distribution of wind speeds and directions converging on a specific spot. Because obviously, local weather completely dictates how smog and pollutants travel from a factory or highway right into our neighborhoods. The windrose ensures these monitors are placed dead center in the path of the pollution.
Let's shift gears to Section 4, health risks and caution. So why does all this complex data collection matter? Because specific pollutants target very specific vulnerabilities in us. Carbon monoxide is exceptionally dangerous for anyone with heart disease. Meanwhile, nitrogen and sulfur dioxide pose immediate, severe threats to people with asthma, as well as children and older adults. This is exactly why checking that AQI is a vital daily habit. Those cautionary statements aren't just generic warnings. They're directly tied to the documented, real-world medical effects of each specific gas.
But listen, it's not just about sensitive groups. Take ground-level ozone, for example. Even if you're a perfectly healthy, athletic individual, heavy short-term exposure to ground-level ozone can cause genuine physical pain when you try to take a deep breath. It inflames your airways, causes coughing, and leaves your lungs way more susceptible to infection. When that AQI hits purple or maroon, absolutely everybody is at risk, no exceptions.
And finally, let's bring it all home. Section 5, Personal Sensors and Apps. We are living in an incredible era of citizen science right now. Low-cost, internet-connected personal sensors, like the air quality egg or purple air monitors, are popping up in backyards everywhere. People are literally carrying portable monitors down busy streets. These devices are continuously sampling the air and crowdsourcing that data online, feeding almost real-time measurements straight to the futuristic dashboards and smartphone apps we rely on every single day to decide if we should go for a run.
But okay, I'm sure a lot of you have experienced this exact mystery. You look at your phone during a super hazy, smoggy day, and your app shows a perfectly green, safe AQI. It leaves you wondering, wait, why doesn't my app match the actual hazy sky right outside my window? What is going on there?
Well, there are a few genuinely fascinating reasons for this disconnect. First off, your app might just be pulling data from a nearby monitor that only tracks ozone, while the haze you're actually seeing is PM 2.5 particle pollution. Second, that haze might honestly just be harmless high humidity, literally just thick water vapor in the air. And finally, during events like wildfires, smoke plumes move incredibly fast. An uncalibrated low-cost sensor grabbing frantic 1-minute snapshots might show wild spikes or completely miss the plume as the wind shifts.
The EPA's official stance on this super fast data is really interesting. They state that health studies do not tell us what a single minute of exposure to a pollutant may mean. The official AQI is actually based on longer exposures that truly correlate to documented health effects. This is exactly why the EPA uses their standardized nowcast system. It beautifully smooths out the data over time, rather than relying on uncalibrated 1-minute spikes from a single backyard sensor. It simply gives you a much truer, more reliable picture of the actual threat.
So, we've explored the global networks, the brilliant physics of capturing microscopic threats, and the real-time data flowing right into our hands. As we envision a sustainable future filled with vibrant green spaces and clean transportation, the question is, armed with this incredible science, how will you use this data to protect yourself and your community the next time the sky turns hazy? I'm Dr. Chem, stay curious, and thanks for joining me on The Explainer.